I will describe some benefit we had to do some optimization on the GYSELA application. And this work is a joint work between CEA, which is the French Agency for Atomic Energy, INERIA, and BSC in Spain. So firstly, I will describe quickly the GYSELA code. So the GYSELA code stands for Gyrokinetic semi-Lagrangian code. So the aim is to describe the plasma that takes place into a tokamak. So you have here a picture of the ITER tokamak, which is currently being built in France. And we want to describe the turbulence and the transport that happens in the plasma in this tokamak. So mainly we will describe ITG instabilities, and these instabilities, like others, has the property to limit plasma performance, and we hope to have the best performance we can in this kind of tokamak. So we should investigate and model the plasma in order to reduce this turbulence effect. So the main equation we are solving is the Vlasov equation in 5 dimensions. I will explain that afterward. And the Poisson equation in 3 dimensions. So there are other gyrokinetic codes that are modeling same kind of things, like GEAN, ORB5, and ELMfire in Europe. So here is a sketch of the geometry we are using. So you have a torus with 3 dimensions. So R, the radial dimension, and then theta and phi, the angular dimensions. And you have a view of a poloidal cut at the right-hand side of the turbulence that are developing inside this cut. And you have also in this modeling a 3 dimension in velocity. So it's a very high dimensional problem. Thanks to the gyrokinetic theory, we can go from 6D to 5D. So we take 2 variables and replace it by a single variable. And then we have a 5D problem, plus time. So the main unknown is a distribution function, f, that describes the particle distribution function. And then you have the electric potential, phi, which have 3 dimensions, the 3 special dimensions, so r, theta, and phi. So the Vlasov equation here with transport mainly at left, and at right collisions and source that can be added or skipped with the kind of simulation we want. So that's the 5D equations that we are solving, the main costs. And then the Poisson equation, which is quite complex, but you have in blue the simple things that you have to look at. So the Laplacian of phi equal an integral with f inside, so Laplacian phi equal right-hand side. So how it is solved? So here, for simplification, I will consider only the Vlasov part, so with no right-hand side term. So you have mainly transport equations. And we use a strong splitting. So what does it mean? We have directional advections. So here you see 3 simplified advection with advection along the phi direction, advection along the v parallel directions, and an advection along r plus theta dimensions. So the big Vlasov equation is solved with these simple operators. We use a semi-Lagrangian scheme that I will not describe here, which is an explicit scheme. So mainly the property that is interesting is that there is no CFL condition, so we can have a quite large time step with this scheme. So the main cost of the application is interpolations because of the semi-Lagrangian scheme. We will see that afterwards. So the global view of what is going on inside the application, we have a time loop, and inside the time loop we have some integrals to go from the distribution function f to the ionic density ni. Then with the Poisson equation we transform this ionic density in the electric potential phi. We do some outputs on disk to see what is going on, and then we push particles. So we solve the Vlasov equation, take the potential and the distribution function, and compute the next time step for the distribution function. So this code is a Fortran 90 code with hybrid parallelism MPI plus OpenMP. So the parallelization we use is along the mu r and theta direction, and this parallelization is true in many parts of the codes except some parts. So we have to change of domain decomposition. The main properties, the work is well balanced between processors, very well balanced, and the only overhead we have is mainly MPI communications. We have also an OpenMP fine-grained parallelization, and it competes with MPI, but it brings some advantages because it avoids MPI communication costs. So here is some example of what is going on in one single step, which is the advection along the variable phi. So you have three loops on mu, r, and theta that are parallelized with MPI. So the first loop is over mu, and we have one MPI communicator per mu value. Then inside this domain decomposition, we have a parallel loop over theta with OpenMP. And then inside three main computations, so computing the displacement, delta phi, and then compute the spline representation of the distribution function along phi direction, and then we interpolate, so taking care of the displacement and of the spline coefficient in order to advance in time. So very simple example to show how it works. So now I will describe how changing of algorithm in terms of domain decomposition can change the performance. So I will compare allow exchange to transpose approach. So firstly, allow exchange. So here you have the same this domain decomposition in the Vlasov solver for each step. So 1D advections and the 2D advection. And with this domain decomposition, we have here in the 2D advection some communication to exchange data on the border of the subdomain to perform the interpolation. So with this allow exchange in r and theta direction, we have a constraint that is added, which is a CFL-like assumption. So the time step is constrained by the space discretization and the velocity. What is the data we exchange practically? So you have here the subdomain that we have in the MPI process in gray. So a subdomain in R and theta. and all the point in V parallel and phi. And for the halo exchange algorithm, we have to add 3 points here in R and theta, and these points are typically received from other MPI processes. The communication cost of this algorithm is something proportional to nr plus n theta times n phi and V parallel n mu. So it's proportional to the perimeter of the subdomain. The other approach is to transpose. So after the first 1D advection, we transpose the distribution function and we change of domain decomposition. So instead of mu r and theta, we have mu phi and V parallel. So with this approach, we have no constraint on time step delta t, so it's quite useful. But we add some communication cost in the transpose step. So what is exactly this transpose step? So we have at left hand side the subdomain we have on the MPI process with a subdomain in R and theta and all points in V parallel and phi. And we are going to subdomain with phi and V parallel for the domain decomposition and all points in R and theta. So here the communication cost is proportional to nr times n theta, n phi, and V parallel n mu. So here the difference is nr times n theta compared to nr plus n theta. So we have a look now on the performance on data structures that takes 1 terabyte distributed over all the processes. So in abscissa, you have the number of cores. In ordinate, you have the time spent for the total simulation in black solid line, and for the 2D advection in red. And you see that with halo exchange compared to transpose approach, the red line is going up, so we have an overhead with transpose approach due to the communication. But on the total time, it's quite not negligible, but not very high overhead. So on the 2D advection with the communication comprised, we have an increase between 30% and 200%. But on the overall runtime, we have only, let's say, 10% of increase. Another machine, so Curie in France, and we have the same kind of results, comparing halo exchange at left-hand side and transpose approach at right-hand side. And the increase of the overall runtime is 12% on big test case, but we have a time step which is enlarged by a factor of 10 or more with the transpose approach. So taking care of the overhead of the transpose approach, but also of the gain we have on the time step, we practically switch to the transpose approach for production runs. So now I will discuss about simultaneous multithreading, which is another optimization we have made recently. So it's another topic. Flops have been increased over the year. So we have we add the NLM switch to Sandy Bridge and the doubling of the peak performance at this time. And then Sandy Bridge to as well has also bring a doubling of flops thanks to AVX2 FPUs. But the question is, the peak performance is increasing, but can we gain something really in application? So we need to take care and to investigate. So recently, the Aswell chip has bring new integer and floating point vector instruction, and especially the multiply and add floating point instruction. So if your code can use this instruction, you can gain a benefit, but if you can't, you know, the peak performance that is doubled, you can't use it really. We have new execution units. This feature, we can use it effectively, and the upgrade of FPUs. And the thing that that I will describe is that now you can really issue 4 instructions by cycle. So we use instruction level parallelism together with SMT to improve performance. So what is going on when we use simultaneous multithreading on Intel processor? We allow 2 threads to execute concurrently on the same core. So we share many resources, so cache memory, execution units, and the front end. But we have some private resources also, like registers. So with this approach, we can avoid wasting cycles. We can hide latencies to access to memory, and we can share FPUs. And this thing is quite important. This approach of simultaneous multithreading is also available on other architectures. And on Aswell processor, we can have at maxima 4 instructions issued by a cycle. So we hope that we can do such thing. So here is a sketch of what is going on a superscalar standard processor and on Aswell processor. So here you see that for each cycle, we can occupy part of the FPUs, so part of the execution unit. But here you have idle execution unit here in white. But with simultaneous multithreading, you can fill up more execution unit. So for this, for the benchmark, we have used the Gyrokinetic machine in Jülich that has Aswell processor. And the GYSELA configuration is 8 threads per MPI process. So we fix that thing. And threads are pinned to cores. So with this pinning, we have positive NUMA effect with cache locality. And we have improved reproducibility of timings, which is quite important for benchmarking. The configuration without SMT is 3 MPI processes per node, so 3 times 8, you have the 24 cores. And with SMT is 6 MPI processes per node. So we modify the domain decomposition in order to get these 6 MPI processes. And we use Paraver to investigate performances. So the size of the case is here, and you have a strong scaling. So the execution time is divided by 2 between each line, and the benefit of SMT is shown here. So we reduce already the time of execution just with activating SMT. But we can do better. So here is a plot we have with Paraver. The black color here is idle time. And you see here multiple processes, and inside each process you have threads execution. And you can see here some thin lines. So thin lines here in the transpose say that you have one thread doing useful work and others are waiting. Here in this location with the 2D advection, we have small black holes, and one has to investigate why these black holes are here. At the end of the 2D advection, you see that you have small imbalance because of these black things here. And it's quite unexpected because it's a very regular application, so why? And then you see here clearly an MPI barrier, and let's say that we have to remove it if we can. So we use a Paraver tool to investigate performance, and these tools add hardware counters automatically. And what we show is that the IPCs, so the number of instructions per cycle, is between 0.9 and 2.8 without SMT, and can go up to 4 with SMT. So we gain on the number of instructions we issue per cycle with SMT. So SMT is really useful to use FPUs at most. So this thing I've already talked about. So we have small load imbalances due to SMT because you have shared resources with SMT and NUMA effects. So for a very irregular code like the one we have, you have to strangely balance the work, which is quite unexpected. Here you can look at very fine grain with Paraver. So here for the transpose operation, you have an MPI barrier. And just next the MPI barrier, you have here this operation that takes much time on some threads, and which is not exactly the same time as other threads, and it is unexpected because the work is exactly the same. So we have to adapt to some kind of heterogeneity coming from the hardware and not from the software. So the solution we found is to fuse, in the 2D advection, is to fuse OpenMP regions. That's why we have many black holes in the 2D advection. So in fusing this OpenMP region, we can avoid overheads to enter and escape OpenMP region and avoid any synchronization that are competing with SMT that introduce some heterogeneity. We also remove some MPI barriers and collective in order to group them, and then it permits to limit the impact of synchronization on the different steps. For the transpose step, we have seen that there is some single threads activated and other doing nothing. It's a problem of copy. So in this step, we copy data, send data, and then copy back what we have received. And the solution is just to use OpenMP for copying the data, and it's quite better timings. So here is the solution and the Paraver plot. So we have here the transpose, which is much shorter because of the OpenMP for copying data. You have the 2D advection without black holes because we have fused OpenMP region. And then the diffusion operation that takes place after the 2D advection is not glued to the advection without MPI synchronization. So we have gain on each steps. Now, if we compare the execution we have with SMT compared to the first timings we have without SMT, we see that we have improved the timings a lot. And what is also very important is that the more we have cores, the more we gain. So we have the best results here for the largest configuration, so it helps to scale also. So I'm almost done. Conclusion, so we have a very scalable tool. The transpose algorithm, it is quite counterintuitive, but it helps, and we have a shorter time to solution. For the new HPC networks, we can handle a tripling of communication costs, and the transpose approach will be also the best. With SMT and Paraver tool, we can improve performance a lot in a new architecture. And the thing which is quite strange is that now the architecture is quite heterogeneous, and we have to adapt workload for a very balanced application. And today and tomorrow, we will need updated tools to dive into perf analysis and try to optimize on new architectures. Thank you for your attention.